All right, hi everyone. We're going to cover 11.4 today and talk about a couple of terms here. The first, well, two main terms. That's not a highlighter, duh. Mutually exclusive, you may have heard that term. Two things are mutually exclusive, and then inclusive. So we're talking about mutually exclusive and inclusive events and what those two things mean. So that's what we covered today, along with calculating their probabilities of events that are mutually exclusive or inclusive. So I'll do a little warm up here. And remember, when we are working in math and we have the word or, we almost always tie that or word with adding. So in this case, let's calculate some probabilities of choosing a card from a deck and the probability that the card chosen is a 5 or a king. All right, so, well, how many 5s or kings are there? So if you look at your deck of cards, there are 4 5s, right? And there are 4 kings. So probability of drawing one card and that card being either a 5 or a king is going to be 4 plus 4, which is 8 out of total 52 cards in the deck. So you're just adding those probabilities. Really, you could just be 4 out of 52 plus 4 out of 52, right? The probabilities separately, we're adding them together, and they're totaling up 8 out of 52, which that would reduce. So if you want to reduce it, that would be 2/13. Okay, similar question here. Probability of a face card or a 2. So in this case, how many 2s are there? There's 4. And face cards, there are 12. So in all, there are 12 plus 4, or 16 different possible cards that would fit that criteria, right? 12 face cards, 4 2s, which would leave a total of 16 out of 52. Or if you divide both those by 4, that would be 4 out of 13. Okay, good deal. Same question. We got a red 4. Choose a red 4 or a prime. Well, how many red 4s? So it looks like there's 1, 2, and then a prime number. Okay, well, there's a 1, 2, 3, 5, 7. I believe that's all of them. So how many is that? 1, 2, 3, 4, 5, 20 plus 2 more, 22. I believe that's 22 out of a total of 52. So 22 out of a total of 52, which divide that in half, that would be 11 out of 26. Anyway, just getting back, thinking in the right mindset there, and or would be, if you're calculating something with 5 or a king, you're adding them up. So let's talk about a mutually exclusive event. So a simple event is an event that describes a single outcome, and a compound event is an event made up of 2 or more simple events. Huh? Sounds a little confusing. So let's look at some examples, I guess. But mutually exclusive events are events that cannot both occur in the same trial of an experiment. Again, a lot of these math definitions and stuff, they don't make great sense unless you look at an example. So they give you an example of rolling a 1 and rolling a 2 on a same roll of one number cube, one die. Is it possible to roll a 1 and a 2? No, it's not. If you roll it, if you're only rolling one die, not possible. So we would consider those events to be mutually exclusive. And if you look at the Venn diagram over here, that's what these things are. These are Venn diagrams. I'm pretty sure you've seen them before. But if you haven't, that's referring to this diagram with this rectangle, these two circles. And so the one circle, event A, represents event A, and the other circle represents event B, and there's no overlap. They can't happen at the same time. All right. So the probability of A or B, if they're mutually exclusive, is going to be just the sum of the probabilities separately. So probability of A or B is equal to just the probability of A plus the probability of B because they're mutually exclusive. Okay. So take a look at some mutually exclusive examples here. Group of students is donating blood during a blood drive. A student has a 9/20th probability of having type O blood and a 2/5 probability of having type A blood. Explain why the events type O and type A are mutually exclusive. Well, you can't be both, right? I mean, you're either one or the other. You're not both. So if you're not both, you're either one or the other. It's mutually exclusive. I spelled your wrong. There we go. You are. So what's the probability that a student has type O or type A blood? Well, you just add them up. 9/20ths plus, what is that? 8/20ths. If I get common denominators, 2/5 is 8/20ths, which would be a total of 17 out of 20. So there's a 17 out of 20 chance that if you pick one student, they have either type A or type O. So there is no overlap in those events. I'm just going to make a little Venn diagram of that real quick. So Venn diagrams, remember, if you haven't seen these, because I should probably, holy cow, that is a crappy rectangle. Ooh, that's a good one. All right, so if you have not seen a Venn diagram, I'm going to show you one here. This Venn diagram is mutually exclusive. These events are mutually exclusive events. So in the Venn diagram, they're not going to overlap at all. Those circles are going to be separated. No, they're not the same, but if they did have some outcomes in common, then I could take those circles and they would overlap. Holy cow, what did I do? So sometimes if they're not mutually exclusive, then they look like this and they have elements in common. But these have nothing in common, so they're separated. So if there was 20 students that we had in this class, 9 of them would have type A, or no, type O, and 8 of the 20 would have type A, and 3 of them would have neither A or O, so it would be out on the outside of the circles, but inside the rectangle. So that would be a whole universal set of 20 students. But, we didn't really need a Venn diagram for that, but it's good to show you. They're a very useful tool to help us see what's going on here. All right, each student cast one vote for senior class president. Of the students, 25% voted for Hunt, 20% for Klein, and 55% for Villa. Student from the senior class is selected at random. Explain why the events voted for Hunt, Klein, or Villa are mutually exclusive. Well, I think it's because you get one vote for one student. Okay, you can't vote for more than one. So it has to be one person you vote for. So the probability a student voted for Klein or Villa, remember, or means we're going to add, and these are mutually exclusive, so we can just add them together, and that's our probability of one or the other. So 55 for Villa, 20% for Klein would give me a total of 75% that one student voted for one or the other. Okay, those events are mutually exclusive. There are no overlap there. On the flip side of that, inclusive events are events that have one or more outcomes in common. For example, you roll a number cube. The outcome would be rolling an even number. Well, rolling an even number would be a 2, 4, or 6. And rolling a prime number would be 2, 3, or 5. Okay, so I'm starting to think maybe I goofed that problem up earlier. I don't know if 1 is prime or not. If I did that, whoops, forgot about my prime definition. But either way, this particular set, these two sets have an element in common, 2. 2 is both prime and it is an even number. Okay, so if 2 is in both, you got to be a little careful on how you add these up. Because let's just say we wanted to know the probability of rolling an even number or a prime number. Well, let's just say you calculated that and you're like, okay, well, how many even numbers are there? 3 out of 6. Plus, how many prime numbers are there? 3 out of 6. Oh, there's a 100% chance that I'm going to pick an even or a prime number, but not really, because 1 is not even nor prime. So what happened is you accidentally double counted the 2. So for that reason, when we are calculating probabilities of inclusive events, we have to be careful to subtract the probability of A and B, which is this intersection of the two circles right here. So you got to be careful if you're not going to make the picture. Now here, I will say, we have the picture here. So if you just have the picture, it's actually kind of easy. You just go, all right, I got 1, 2, 3, 4, 5. There's 5 different possibilities. You just count them right up or add them all up. But if you don't do the picture, then you have to be really careful to not double count the intersection, so you'd have to subtract that off. All right, so let's look at a few examples there. Find the probability on a number cube of rolling a 4 or an even number. Well, let's just make sure. Let's just draw a quick little Venn diagram of this. That's, I think, the best way to do these is to draw a Venn diagram. So these events are going to be inclusive, so they are going to have some elements in common. I should be able to duplicate that. There we go. Just want to move it. Gosh, what the heck? There we go. Good enough. All right, so rolling a 4 or an even number. Well, are they inclusive or exclusive? Mutually exclusive. They are inclusive. So because they're inclusive, that means there is an overlap, so we need to determine that first. Well, rolling a 4 only has one outcome. And so rolling a 4 or rolling an even, the one element that is in both is the 4. Okay? The other evens that are not 4s would be 2 and a 6. And so my Venn diagram would look like that. There's a 2, a 4, and a 6 all in the even, and the 4 is in the overlap. And then on the outside, we'd have all the odds, 1, 3, and a 5. All right, so what's the probability that you roll a 4 or an even number? Well, how many are there? There's 2, 4, or 6. There's really only 3 elements. So if I have the picture, I can just look right at it and go 3 out of 6 or 1/2. But if you didn't do the picture, you might think, okay, probability of rolling a 4 is 1/6, plus the probability of rolling an even number is 3/6. And so it would be 4/6, but not so fast. You double counted the 4, so you have to subtract the intersection of the 2 off there. So I personally just think if you can make a Venn diagram, then you can just go ahead and add up all of your possibilities in your Venn diagram. Let's do another one here. Rolling an odd number or a number greater than 2. Okay, well, let's see. Odd or number greater than 2. Are there any that are both? Odd numbers greater than, yeah, there are 3 and 5 are both. So that's in the overlapping area. Are there any odd numbers that aren't greater than 2? Yeah, there's a 1 that goes over there. And any numbers greater than 2 that aren't odd? Yeah, 4 and a 6. So if you want to know now the probability of an odd number or a number greater than 2, all you have to do is just go and count them up. 1, 2, 3, 4. There's 5. It's 5 possibilities. So 5 out of a total. Oops, I forgot to put my other one possibility that doesn't fit in either one. That's the 2. So that's on the outside. But anyway, 5 out of 6 is the probability of rolling an odd number or a number greater than 2. All right, I'm going to call a quick timeout here and just talk about a couple things with the Venn diagram because I'm not sure. I still want to assume that you all know this. So with the Venn diagram, let's see, that was crappy. Okay, you add a Venn diagram here, right? Let's just say this event is A and this event is B. All right, let's talk. I'm going to duplicate this too. So let's see, let me go. All right. So A or B is everything inside the whole circles, including the overlap, right? So whatever is in there, all of that totaled up is the size of A or B. And that would be represented with a U like this. It's called the union. Okay, so that's the union of A or B. And that is the OR. Okay, and is this spot right here. This is the intersection. So that is the and the symbols there are A. Oh, my garage heater just kicked on. Sorry about that. A and B. That's the intersection. All right, so A or B is everything inside all the circles, and A and B is just that overlapping area. All right. So right now we're talking about the OR, the whole Venn diagram. Card is drawn from deck of 52. Find the probability of each. Drawing a king or a heart. Well, this one I'm not going to make the picture. Now I'll show you just what we have to do if we don't make the picture. So how many kings are there in the deck? Probability of a king, 4 out of 52. Plus, how many hearts are there in the deck? Well, there's half of them, so 26 out of 52. Just kidding, there's not half. What are you talking about? There's 13 out of 52. Okay, but you know what? You got to be careful because being a king and being a heart are not mutually exclusive. They are inclusive. And so therefore, they share one card, the King of Hearts. It belongs in both of those events, I guess you could say. So the king and the heart, the King of Hearts, needs to be subtracted. Otherwise, you're double counting it. So it'd be 4 plus 13, which is 17 minus 1, which is 16 out of 52, which reduces to 4/13. Okay. If you drew the picture, let's draw a little picture quick. Draw the picture. You got, oh, not that. Here, I'm just going to be sloppy for a second. You got the kings. You got the hearts. They're not mutually exclusive, so there's one king of hearts that is in the overlap. And there's 3 kings that are not hearts. And there's 12 hearts that are not kings. So if you add all those up, what do you get? You add all those together. You get 3 plus 1 plus 12. You get a total of 16. So you either draw the picture and then you can just add them all together. If you don't draw the picture, you got to be careful not to forget to subtract the overlap. Okay, I think we're almost done here. I'm drawing a red card, which is a harder diamond, or a face card. All right, this time I'm just going to make the picture. So a red card, or, what is it, or a face card? All right, oops, here we go. Let's call this the red card. Call this the face card. Are there any red cards that are face cards? Yeah, half of them are. Okay, so half of the face cards are red cards, and there's 12 face cards. So that means there's 6 that are red, there's 6 that are not red, and out of all the 26 red cards, 6 of them are face cards and 20 aren't. So we have a total now. If we want to find out either red card or face card, you just add all these up. 20 plus 6 plus 6 is a total of 32 out of 52, which those divide both by 4, which reduces to 8/13. So I personally just like making the Venn diagram, making a picture. It might take a little bit longer, but I think it's easier to just add them all up, and you don't forget to subtract the middle part. All right. So probability of a spade or less than 6. Okay, let's just draw the picture. There is overlap there because there's going to be spades that are less than 6. So how many spades are there that are less than 6? So we got the ace, the 1, the 2, 3, the 4, the 5. So there's 5 of them. Then there's 8 spades that are not less than 6. Consider the face cards to usually be 10. So that would be the spades. And the numbers of cards that are less than 6 in the whole deck, well, there's going to be 1, 2, 3, 4, 5, right? So there's 5 of them times 4 suits, so that's a total of, I believe, 20. Oh, wait a minute. 20 total. So there's 20 cards here. I'm going to go back up. You might be wondering about this here. How many cards in total are less than 6? Well, there's going to be all those, which is 5 times 4, which is 20 in total. But I already accounted for all the spades, so I already accounted for 5 of them. So actually, I made a mistake there. That shouldn't be 20. That should be 15. So now when you want to find out the probability of a spade or a card less than 6, you add all those together and you get 28. 28 out of 52, which reduces to be 7 out of 13. So that's a little bit about mutually exclusive or inclusive. And, personally, I like to just make the Venn diagrams if I can. But if you don't make the Venn diagrams, then make sure you don't forget to subtract out that intersection part. All right? But that's it for today.